Welcome back to Science with Sleepy. Have you ever looked up at the sky and wondered what it would be like if there were two suns? What if tomorrow morning, when you wake up, you see not one but two bright glowing orbs rising over the horizon? Would it be amazing? Scary? Or maybe a little bit of both? Today, we're going on an incredible journey. We're going to explore one of the wildest what-if questions in all of space science. What happens if two suns rise tomorrow? We're not just going to imagine it, we're going to learn the real science behind it. We'll discover what our sun actually is. We'll meet planets that really do have two suns. And we'll find out exactly what would happen to Earth, to you, to everything, if a second sun appeared in our sky. This is going to be a big adventure. We'll travel through space, learn about stars, and discover some mind-blowing facts about our own sun. Facts that will make you see that bright ball in the sky in a whole new way. So get comfortable, take a deep breath, and let's begin our journey into a world with two suns. Ready? Let's go. Chapter 1. Our amazing sun, the star we call home. Before we can imagine two suns, we need to understand the one we have. Our sun is incredible. It's not just a bright light in the sky, it's a star, a real live burning star. Here's something that might surprise you. The sun is actually a medium-sized star. It's not the biggest, it's not the smallest, it's right in the middle, but to us, it's everything. Without it, life on Earth wouldn't exist. Let me tell you about our sun. It's huge. I mean really huge. If you could line up 109 Earths side by side, that's how wide the sun is. Think about that. Our entire planet could fit inside the sun more than 1 million times. The sun is so big that it contains 99.86% of all the mass in our entire solar system. Everything else, all the planets, all the moons, all the asteroids, that's just 0.14%. The sun's diameter is about 864,000 miles. That's 1.4 million kilometers. To put that in perspective, if the sun were a basketball, Earth would be about the size of a tiny seed. That's how much bigger the sun is than our planet. The sun's volume is enormous. You could fit 1.3 million Earths inside the sun. That's a lot of Earths. If you tried to count them, it would take you forever. Even though the sun is so huge, it's actually pretty average for a star. There are stars much bigger out there. The sun's mass is about 2 times 10 to the 30th power kilograms. That's 2, followed by 30 zeros. It's a number so big it's hard to imagine. But here's a way to think about it. The sun weighs as much as 333,000 Earths combined. That's a lot of weight. The sun's gravity is incredibly strong. At the surface, the gravity is about 28 times stronger than Earth's gravity. If you could stand on the sun, you'd weigh 28 times more than you do on Earth. But of course, you can't stand on the sun. It's too hot, and there's no solid surface anyway. The sun's escape velocity is about 618 kilometers per second. That's how fast you'd need to go to escape the sun's gravity. On Earth, you only need to go about 11 kilometers per second. The sun's gravity is so strong that it holds all the planets in orbit, even though they're millions of miles away. The sun is about 93 million miles away from Earth. That's 150 million kilometers. That might sound far, but in space terms, it's actually pretty close. Light from the sun takes about 8 minutes and 20 seconds to reach us. So when you look at the sun, you're seeing it as it was 8 minutes ago. Not too long, right? But still, you're looking into the past. The sun is made mostly of hydrogen and helium. About 73% is hydrogen. About 25% is helium. The rest is tiny amounts of other elements like oxygen, carbon, nitrogen, neon, magnesium, silicon, sulfur, and iron. But here's the cool part. The Sun is constantly turning hydrogen into helium. This process is called nuclear fusion. The Sun's composition changes over time. As it burns hydrogen, it creates more helium. Right now, the core is about 35% helium. But the outer layers are still mostly hydrogen. This is because the fusion only happens in the core, not throughout the entire Sun. The Sun contains about 10 to the 57th power atoms. That's a 1 followed by 57 zeros. It's an unimaginably large number. Most of these atoms are hydrogen, but even the tiny fraction that's other elements is enormous. For example, the Sun contains more iron than the entire Earth weighs. That's a lot of iron. Deep inside the Sun, at its core, the temperature is about 27 million degrees Fahrenheit. That's 15 million degrees Celsius. It's so hot that atoms can't stay together. They smash into each other with incredible force. When hydrogen atoms collide, they fuse together and create helium. This releases enormous amounts of energy. That energy travels outward from the core, through layers and layers of the Sun, and finally escapes as light and heat. The core is incredibly dense. The pressure there is about 250 billion times the pressure at sea level on Earth. Under these extreme conditions, hydrogen atoms are forced together. They overcome their natural repulsion and fuse. This is what powers the Sun. Every single second, the Sun converts about 600 million tons of hydrogen into helium. That's right, every second. 600 million tons. And it's been doing this for about 4.6 billion years. The Sun has used up about half of its hydrogen fuel. It has enough left to keep burning for another 5 billion years. To put that in perspective, 600 million tons is about the weight of 100,000 elephants. Every second. That's how much hydrogen the Sun is burning. And it's been doing this for billions of years. The Sun is an incredibly efficient energy machine. The energy produced by nuclear fusion is enormous. Every second, the Sun produces about 3.8 times 10 to the 26th power watts of power. That's enough energy to power all of human civilization for hundreds of thousands of years, and the Sun does this every single second. The energy from fusion takes a long time to reach the surface. Photons, particles of light, are created in the core, but they don't travel straight out. They bounce around, colliding with atoms, being absorbed and re-emitted. It takes about 100,000 to 200,000 years for energy to travel from the core to the surface. Then it takes just 8 minutes to reach Earth. This means the sunlight you see today was actually created in the Sun's core tens of thousands of years ago. You're looking at ancient light. Light that has been bouncing around inside the Sun for longer than humans have existed. The surface of the Sun, called the photosphere, is much cooler than the core. It's only about 10,000 degrees Fahrenheit, or 500 degrees Celsius. That's still incredibly hot, but compared to the core, it's almost chilly. Well, not really, but you know what I mean. At that temperature, iron would be a gas, not a solid or liquid. The photosphere is about 300 miles thick. That's where most of the Sun's visible light comes from. It's not a solid surface, but a layer of gas that's dense enough to be opaque. When we look at the Sun, we're seeing the photosphere. The photosphere has a grainy appearance. This is called granulation. It looks like rice grains or bubbles. These are convection cells, where hot gas rises from below, cools, and sinks back down. Each granule is about the size of Texas. They last for about 8 to 20 minutes before being replaced by new ones. Above the surface is the Sun's atmosphere. It has layers. The chromosphere is a thin layer of hot gas, about 1-200 miles thick. It's red in color, which is why it's called the chromosphere, meaning sphere of color. During a solar eclipse, you can sometimes see it as a red rim around the Sun. The chromosphere is hotter than the photosphere. reaching about 14,000 degrees Fahrenheit. But it's much less dense. The gas there is so thin that it's almost a vacuum compared to Earth's atmosphere. Above the chromosphere is the corona, the Sun's outer atmosphere. And here's something weird. The corona is actually hotter than the surface. Way hotter. It can reach millions of degrees. Scientists are still trying to figure out why. It's one of the Sun's biggest mysteries. The corona extends millions of miles into space. It's visible during total solar eclipses as a beautiful white halo around the Sun. But normally it's too faint to see, because the photosphere is so much brighter. The corona's temperature varies, but it can reach 2 to 3 million degrees Fahrenheit in some regions. That's hundreds of times hotter than the surface. This shouldn't be possible according to basic physics. Heat should flow from hot to cold, not the other way around, but somehow, the corona is being heated by something. Scientists think it might be related to the Sun's magnetic field, but they're not sure exactly how. The Sun rotates, but not like a solid ball. Different parts rotate at different speeds. At the equator, it takes about 25 days to complete one rotation. Near the poles, it takes about 35 days. This is because the Sun is made of gas, not solid rock. It can twist and turn in ways that would be impossible for a solid object. This differential rotation is important. It means the Sun's equator moves faster than its poles. This creates a shearing effect, like rubbing your hands together. This shearing helps generate the Sun's magnetic field. Without it, the Sun wouldn't have the complex magnetic field it has. The Sun's rotation speed at the equator is about 400 miles per hour. That's fast. But because the Sun is so huge, it still takes 25 days to complete one rotation. If Earth rotated that slowly, a day would last 25 times longer. But Earth is much smaller, so it rotates much faster. The Sun has a magnetic field. It's incredibly powerful. This magnetic field creates sunspots, solar flares, and coronal mass ejections. The magnetic field is generated by the movement of charged particles in the Sun's interior. As the Sun rotates, these particles create electric currents, which in turn create magnetic fields. The Sun's magnetic field is complex and constantly changing. It's not like a simple bar magnet. It has multiple poles, and they shift over time. Every 11 years, the magnetic field flips. The North Pole becomes the South Pole, and vice versa. This is related to the sunspot cycle. Sunspots are dark patches on the Sun's surface. They're cooler than the surrounding area, but still incredibly hot. About 600–700 degrees Fahrenheit compared to 10,000 degrees for the surrounding photosphere. They appear dark because they're cooler, not because they're actually dark. If you could see a sunspot by itself, it would still be incredibly bright. Sunspots can be huge. The largest ones can be bigger than Earth. Some have been observed that are 50,000 miles across. That's more than 6 times the diameter of Earth. They can last for days, weeks, or even months before fading away. Sunspots appear in pairs, or groups. They always come in pairs with opposite magnetic polarities. One will have a north magnetic pole, the other a south magnetic pole. This is because they're created by magnetic field lines emerging from and returning to the Sun's interior. Sunspots appear in cycles. About every 11 years, the Sun goes through a cycle of high and low sunspot activity. At solar maximum, there can be hundreds of sunspots visible at once. At solar minimum, there might be days or weeks with no sunspots at all. The last solar maximum was in 2014. The next one is expected around 2025. The sunspot cycle affects Earth in many ways. During solar maximum, there are more solar flares and coronal mass ejections. This can disrupt satellites, power grids and radio communications. But it also creates more beautiful auroras in the polar regions. Solar flares are sudden bursts of energy from the sun's surface. They can release as much energy as millions of atomic bombs. The largest flares can release 10 to the 25th power joules of energy. That's equivalent to billions of megatons of TNT. But don't worry. Earth's atmosphere protects us from most of this energy. Sometimes, though, solar flares can disrupt satellites and power grids. Solar flares are classified by their strength. X-class flares are the strongest. They can cause radio blackouts and long-lasting radiation storms. M-class flares are medium strength. They can cause brief radio blackouts. C-class flares are weak and usually don't affect Earth much. Solar flares happen when magnetic field lines near sunspots get twisted and snap. This releases enormous amounts of energy in the form of X-rays, ultraviolet light, and charged particles. The energy travels through space at the speed of light, reaching Earth in about 8 minutes. The largest solar flare ever recorded was in 1859. It's called the Carrington event, named after the astronomer who observed it. It caused telegraph systems to fail all over the world. Some telegraph operators even got electric shocks. If a similar flare happened today, it could cause trillions of dollars in damage to satellites, power grids, and communication systems. Solar flares can create beautiful auroras, but they can also be dangerous. The radiation from flares can harm astronauts in space. It can damage satellites. It can disrupt GPS signals. It can even cause power outages on Earth. In 1989, a solar flare caused a massive power outage in Quebec, Canada, leaving millions without power for hours. The sun is constantly sending out a stream of particles called the solar wind. These particles travel through space at incredible speeds, typically 250 to 500 miles per second. That's fast. Really fast. The solar wind is made mostly of protons and electrons, the same particles that make up atoms. The solar wind flows outward in all directions from the sun. It extends far beyond the orbit of Pluto, creating a bubble called the heliosphere. This bubble protects our solar system from cosmic rays coming from other stars. The edge of the heliosphere is called the heliopause, and it's about 11 billion miles from the sun. The solar wind varies in speed and density. Fast streams come from coronal holes, regions where the sun's magnetic field opens into space. Slow streams come from other regions. When these streams interact, they can create space weather that affects Earth. When the solar wind reaches Earth, it interacts with our magnetic field. Most particles are deflected around the planet. But some get trapped in the magnetic field and spiral toward the poles. When they hit the atmosphere, they create beautiful auroras, the northern and southern lights. Auroras are one of nature's most beautiful displays. They appear as dancing curtains of light in the sky, usually green, but sometimes red, blue or purple. They're caused by charged particles from the sun exciting atoms in Earth's upper atmosphere. The colors depend on which atoms are being excited, and at what altitude. The solar wind also creates a tail behind Earth, like a comet's tail. This is called the magnetotail. It extends millions of miles into space, always pointing away from the sun. The magnetotail is where some of the most interesting space weather happens, including magnetic reconnection events that can cause geomagnetic storms. The sun is about 4.6 billion years old. That's middle-aged for a star. It will keep shining for about another 5 billion years. Then it will start to change. It will grow larger and become a red giant. Eventually, it will shrink down to become a white dwarf. But that's billions of years in the future. We don't need to worry about it. Scientists determine the sun's age by studying meteorites. Meteorites are pieces of asteroids that have fallen to Earth. They formed at the same time as the solar system, so they're the same age as the sun. By measuring the radioactive elements in meteorites, scientists can calculate how long ago they formed. This tells us the age of the sun and the solar system. The sun's gravity holds our entire solar system together. Every planet, every moon, every asteroid orbits the sun because of its gravitational pull. Without the sun's gravity, everything would fly off into space. The sun's gravity is what keeps us in orbit, what keeps the planets in their paths, what keeps the solar system stable. Gravity gets weaker with distance. The farther you are from the sun, the weaker its gravitational pull. But it never completely disappears. The sun's gravity extends far beyond the orbit of Pluto, affecting objects in the outer solar system, and even in the Oort cloud, a distant region of comets. The sun's gravity also affects the shape of space itself. According to Einstein's theory of general relativity, massive objects warp space and time. The sun warps the space around it, creating a gravitational well. Planets orbit the sun by following the curves in this warped space. It's like rolling a marble around a bowl. The marble follows the curve of the bowl. The sun produces energy through nuclear fusion. This is the same process that powers hydrogen bombs. But the sun does it continuously, in a controlled way, deep in its core. The energy takes thousands of years to travel from the core to the surface. Then it takes just 8 minutes to reach Earth. The sun is actually white, not yellow. It appears yellow from Earth because our atmosphere scatters blue light. This is called Rayleigh scattering. It's the same effect that makes the sky blue. Blue light has a shorter wavelength, so it gets scattered more. Red and yellow light have longer wavelengths, so they pass through more easily. If you could see the sun from space, it would look white. The color we see is just an effect of our atmosphere. The sun emits light across the entire electromagnetic spectrum. It produces radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and even gamma rays. Most of the energy is in visible light, which is why we can see it. But there's also a lot of energy in invisible wavelengths. The sun is getting brighter over time. Very slowly, about 1% every 100 million years. This happens because as the sun converts hydrogen to helium, its core gets denser and hotter. This makes the fusion process more efficient. In 1 billion years, the sun will be about 10% brighter than it is today. This gradual brightening has implications for Earth. As the sun gets brighter, Earth will get warmer. Eventually, in about 1 billion years, the sun will be bright enough to boil away Earth's oceans. But that's a long time from now. For now, the sun's brightness is relatively stable, which is good for life on Earth. The sun's brightness also varies slightly over shorter timescales. There are small fluctuations related to the sunspot cycle. When there are more sunspots, the sun is actually slightly brighter, not dimmer. This is because sunspots are surrounded by bright regions called faculae, which more than compensate for the dark sunspots. The sun has no solid surface. It's a ball of hot gas from the core all the way to the edge. If you tried to land on it, you'd just fall through. There's nothing solid to stand on. The sun's core is under incredible pressure, about 250 billion times the pressure at sea level on Earth. This pressure, combined with the extreme heat, is what makes nuclear fusion possible. The sun rotates on its axis, just like Earth. But because it's made of gas, different latitudes rotate at different speeds. This creates something called differential rotation. It's one of the reasons the Sun's magnetic field is so complex. The Sun is moving through space, it's not sitting still. It's orbiting the center of our galaxy, the Milky Way, at about 514,000 miles per hour. That's fast. But it takes about 225 million years to complete one orbit around the galaxy. The Sun is actually pretty average as stars go. There are stars much bigger and much smaller. There are stars much hotter and much cooler. But to us, it's perfect. It's the right size, the right temperature, and the right distance to support life on Earth. The Sun's energy output is called its luminosity. The Sun's luminosity is about 3.8 times 10 to the 26th power watts. That's a number so big it's hard to imagine. To put it in perspective, all the energy humans use in an entire year is less than what the Sun produces in 1 second. The Sun has been studied for thousands of years. Ancient civilizations tracked its movements across the sky. They built monuments aligned with the Sun, like Stonehenge in England and the pyramids in Egypt. They used it to tell time and mark the seasons. The Sun was often worshipped as a god, which shows how important it was to early humans. The ancient Greeks were among the first to try to understand the Sun scientifically. They measured its size and distance, though their estimates were way off. They thought the Sun was much smaller and closer than it actually is. But they were asking the right questions. In the 1600s, Galileo used a telescope to observe the Sun. He discovered sunspots, dark patches on the Sun's surface. This was controversial because people thought the Sun was perfect and couldn't have blemishes. But Galileo's observations proved that the Sun was a physical object, not a perfect celestial sphere. In the 1800s, scientists began to understand that the Sun was a star. They measured its spectrum and found that it contained the same elements found on Earth. This was a huge discovery. It meant that the Sun wasn't fundamentally different from other stars. It was just closer. In the early 1900s, scientists discovered nuclear fusion. They realized that this was how stars produce energy. This solved the mystery of how the Sun could shine for billions of years. Before this, people thought the Sun was burning like a fire, which would have used up all its fuel in just a few thousand years. But we've learned more about the Sun in the last 50 years than in all of human history before that. Modern telescopes and spacecraft have revealed the Sun's secrets. The Parker Solar Probe, launched in 2018, is getting closer to the Sun than any spacecraft before. It's teaching us new things about the solar wind, the corona, and how the Sun works. We now know that the Sun is a complex dynamic object. It's not just a simple ball of fire. It has layers, magnetic fields, and cycles of activity. It's constantly changing, even though those changes happen slowly from our perspective. Understanding the Sun helps us understand other stars, and it helps us understand our place in the universe. The Sun is essential for life on Earth. Plants use sunlight to make food through photosynthesis. This process produces oxygen, which we breathe. Without the Sun, there would be no plants. Without plants, there would be no oxygen. Without oxygen, there would be no us. The Sun also drives Earth's weather. It heats the oceans and the atmosphere. This creates winds, storms, and weather patterns. The Sun's energy powers the water cycle, making clouds and rain possible. Without the Sun, Earth would be a frozen, lifeless rock. The Sun's energy also creates ocean currents. Warm water flows from the equator toward the poles, while cold water flows back. These currents distribute heat around the planet, moderating temperatures. They also carry nutrients, supporting marine life. The Sun is the engine that drives Earth's climate system. The Sun even affects Earth's rotation. The gravitational pull of the Sun and Moon creates tides, which slow down Earth's rotation over time. Billions of years ago, a day was only about 18 hours long. Now it's 24 hours. In the future, days will be even longer. This is all because of the Sun's gravity. The Sun also affects Earth's orbit. Over thousands of years, the shape of Earth's orbit changes slightly due to the gravitational influence of other planets. But the Sun's gravity is the dominant force, keeping Earth in a stable orbit. Without it, Earth would fly off into space. So our Sun is pretty amazing, right? It's huge, it's hot, it's powerful, and it's essential for life. It's been shining for billions of years, and it will keep shining for billions more. It's the perfect star for Earth, providing just the right amount of light and heat for life to thrive. But what if there were two of them? What if tomorrow morning a second sun appeared in the sky? How would that change things? Would it be amazing, scary, or both? That's what we're going to explore next. But first, let's meet some planets that really do have two suns. They exist, they're real, and they're out there, right now, in our galaxy. Learning about them will help us understand what it would mean for Earth to have two suns. Chapter 2: Worlds with Two Suns. They're real. Guess what? Planets with two suns aren't just science fiction, they're real. Astronomers have found them. They exist in our galaxy, right now, as we speak. The first planet discovered orbiting two stars was called Kepler-16b. It was found in 2011 by NASA's Kepler Space Telescope. This planet is about the size of Saturn. It orbits two stars that orbit each other. From the surface of this planet you would see two suns in the sky. Two sunrises. Two sunsets. How cool is that? The discovery of Kepler-16b was a huge moment in astronomy. Before this, scientists weren't sure if planets could form in binary star systems. The gravitational forces seemed too chaotic. But Kepler-16b proved that planets can indeed form and survive in such systems. This opened up a whole new field of study. The two stars in the Kepler-16 system are smaller than our Sun. One is about 69% the mass of our Sun. It's a K-type star, slightly cooler and redder than our Sun. The other is about 20% the mass of our Sun. It's a red dwarf, much smaller and cooler. They orbit each other every 41 days, which means they're relatively close together. The planet Kepler-16b orbits both stars in what's called a circumbinary orbit. It's about 65 million miles from the center of mass of the two stars. That's similar to Venus's distance from our Sun. The planet takes about 229 days to complete one orbit. That's shorter than Earth's year, but longer than Venus's year. From the surface of Kepler-16b, the two suns would appear different sizes. The larger star would look about half the size of our Sun in our sky. The smaller star would look much smaller, about the size of a bright star. They would orbit each other in the sky, sometimes appearing close together, sometimes far apart. The temperature on Kepler-16b is probably around -100 degrees Fahrenheit. That's cold, really cold. The planet is too far from the stars to be in the habitable zone. But it's still fascinating to imagine what it would be like to stand on a world with two suns in the sky. Since the discovery of Kepler-16b, astronomers have found many more planets in binary star systems. Some orbit both stars, like Kepler-16b. Others orbit just one star, with the other star appearing as a bright object in the sky. There might be millions of such planets in our galaxy alone. One interesting example is Kepler 453b, another circumbinary planet. It orbits two stars that are very different sizes. One is similar to our Sun, the other is much smaller. The planet experiences dramatic changes in light as the stars orbit each other. Sometimes both stars are visible. Sometimes one is hidden behind the other. The light levels can vary by 20% over the course of a single day. Binary star systems are actually pretty common. About half of all stars in the universe are part of binary or multiple star systems. Our Sun is unusual because it's alone. Most stars have at least one companion. Binary stars can be different types. Some are close together, orbiting each other in just days or hours. Some are far apart, taking thousands of years to orbit. Some are the same size, some are very different sizes. In close binary systems, the stars can actually transfer material between them. Gas can flow from one star to the other. This can create all sorts of interesting phenomena, like novas and X-ray binaries. In wide binary systems, the stars are far apart. They might not affect each other much. Planets can orbit one star or the other, or both. The possibilities are endless. Having two suns creates challenges. The gravity is more complex. The light and heat patterns are different. The day and night cycles can be strange. Let's think about what that would mean for Earth. If a second sun appeared in our solar system, where would it come from? There are a few possibilities. Maybe a star wandered too close to our solar system and got captured by the sun's gravity. Maybe our Sun was always part of a binary system, and we just never noticed the companion star because it's so far away. Actually, some astronomers think the Sun might have a distant companion. They call it nemesis. It would be a small, dim star, or maybe a brown dwarf, a failed star that never got hot enough to shine. It would orbit the Sun very far away, taking millions of years to complete one orbit. If it exists, we haven't found it yet. But it's possible. If a second sun appeared, the first thing we'd notice is the light. Two suns would mean twice as much light during the day. Well, not exactly twice. It depends on how bright the second sun is and how far away it is. But there would definitely be more light. More light means more heat. The temperature on Earth would rise. How much? That depends on the second sun. If it's similar to our Sun and at a similar distance, Earth would get about twice as much energy. The average temperature would rise dramatically, ice caps would melt, sea levels would rise, the climate would change completely. But wait, there's more to think about. What about gravity? Two suns would mean more gravitational pull. This would affect Earth's orbit. Our planet might be pulled into a different path. The orbit could become unstable. Earth might spiral inward toward the suns, or it might be flung outward into space. Actually, if a second sun appeared suddenly, Earth's orbit would become chaotic. The gravitational forces from two stars would pull Earth in different directions. The orbit would change constantly. Some paths might be stable for a while, but then they'd change again. It would be like trying to walk a straight line while two people are pulling you in different directions. The day and night cycle would be completely different. With two suns, there might not be a true night at all, or night might only happen when both suns are below the horizon. The length of day and night would change constantly as the suns move relative to each other. If the two suns orbit each other closely, Earth might experience regular patterns. Days when both suns are up, days when one is up, days when neither is up. But if the suns are far apart, the patterns would be more complex and less predictable. The seasons would change too. Earth's tilt causes our seasons. But with two suns pulling on Earth, the tilt might change, or the orbit might become more elliptical, creating extreme seasons. Some parts of the year might be incredibly hot, others might be incredibly cold. The tides would be affected. Our tides are caused by the moon and the sun. With a second sun, there would be additional gravitational forces pulling on the oceans. The tides would be stronger and more complex. Coastal areas would experience dramatic changes. Not all binary star systems are bad for planets, though. Some planets in binary systems might actually be in stable orbits. It depends on the masses of the stars, their distance from each other, and the planet's distance from them. For a planet to have a stable orbit around two stars, it usually needs to be far enough away. The planet orbits the center of mass of both stars. This is called a circumbinary orbit. If the planet is too close, the gravitational forces become too chaotic, and the orbit becomes unstable. Kepler 16b is in a stable circumbinary orbit. It's far enough from both stars that their gravity combines into a single, stable pull. From the planet's perspective, it's like orbiting one object, even though that object is actually two stars. But what if Earth suddenly found itself in a binary system? What if a second sun appeared tomorrow? The changes would be immediate and dramatic. First, the sky would look different. During the day, you'd see two bright objects. They might be different sizes, depending on how far away the second sun is. They might be different colors, depending on the second sun's temperature. At night, if there is a night, the sky would be different too. The stars we see would be the same, but the overall brightness of the night sky would be different. There might be two sources of light, making it harder to see faint stars. The temperature would rise. How much depends on the second sun. But even a small increase would have huge effects. Ice would melt, sea levels would rise, weather patterns would change, storms might become more intense, droughts might become more common, plants would be affected. Some plants might get too much light and heat, they might wither and die. Other plants might thrive in the extra light. But the overall ecosystem would be disrupted. Many species would go extinct. Others would adapt or migrate. Animals would be affected too. Many animals rely on day and night cycles. Their sleep patterns, hunting patterns and migration patterns all depend on the regular cycle of light and dark. With two suns, these patterns would be disrupted. Some animals might not be able to adapt. Humans would face challenges. We'd need to adapt to the new conditions. We'd need new ways to stay cool. We'd need to protect ourselves from increased radiation. We'd need to find new ways to grow food. We'd need to deal with rising sea levels and changing weather. Life is resilient, though. If the changes happen slowly over thousands or millions of years, life might adapt. New species might evolve to take advantage of the new conditions. But if it happens suddenly, like tomorrow, the changes would be too fast for most life to adapt. So having two suns would be a mixed bag. It would be amazing to see. It would create incredible sunrises and sunsets. But it would also create enormous challenges. Earth as we know it would change completely. But you know what? Let's not worry about that. Because it's not going to happen, at least, not tomorrow. Our solar system is stable, our sun is alone, and that's probably a good thing. Instead, let's learn more about stars themselves. What are they? How do they form? How do they work? Understanding stars will help us understand what it would really mean to have two suns. Chapter 3: When Two Suns Meet Earth, the Science of What Would Happen. Okay, let's get serious about this. What would actually happen if two suns rose tomorrow? Let's break it down, step by step, using real science. First, let's think about the light. Our sun produces an incredible amount of light. Every square meter of Earth's surface receives about 1,366 watts of solar energy when the sun is directly overhead. That's enough to power a small space heater. Now imagine doubling that. Or maybe even more depending on the second sun. This number, 366 watts per square meter, is called the solar constant. It's the amount of energy Earth receives from the Sun at the top of the atmosphere. But not all of this reaches the surface. About 30% is reflected back into space by clouds, ice, and other surfaces. Another 20% is absorbed by the atmosphere. Only about 50% actually reaches the ground. The amount of light depends on the second sun's brightness and distance. A star's brightness depends on its size and temperature. Bigger, hotter stars are brighter. Smaller, cooler stars are dimmer. The relationship between size, temperature, and brightness is complex. A star twice as big isn't necessarily twice as bright. It depends on the temperature too. Our Sun is a G-type main sequence star. It's yellow-white, medium-sized, and medium temperature. Main sequence means it's in the stable phase of its life, fusing hydrogen into helium. G-type means it has a surface temperature of about 10,000 degrees Fahrenheit. There are hotter stars, like O-type and B-type, which are blue, and cooler stars, like K-type and M-type, which are red. If the second sun were an O-type star, it would be incredibly bright. O-type stars can be 100,000 times brighter than our Sun. But they're also much rarer and shorter lived. If the second sun were an M-type red dwarf, it would be much dimmer, maybe only 1% as bright as our Sun. But red dwarfs are the most common type of star in the universe. If the second sun were similar to our Sun, Earth would receive about twice as much light. But if it were a bigger, hotter star, like a blue giant, it could be hundreds of times brighter. If it were a smaller, cooler star, like a red dwarf, it might only add a little extra light. The distance matters too. Light gets dimmer as you move away from the source. If the second sun were twice as far away as our Sun, it would appear 4 times dimmer. This is called the inverse square law. Double the distance, quarter the brightness. But let's say the second sun is similar to our Sun and at a similar distance. Earth would receive about twice as much energy. The average temperature would rise. Currently, Earth's average temperature is about 59 degrees Fahrenheit. With twice the energy, it could rise to over 100 degrees. That's hot, really hot. The polar ice caps would melt. They're already melting due to climate change, but with 2 suns they'd melt completely and quickly. All that ice would flow into the oceans. Sea levels would rise by hundreds of feet. Coastal cities would be underwater. Much of the land we know would disappear. The oceans would heat up. Warmer water holds less oxygen. Marine life would struggle. Coral reefs would die. Fish populations would crash. The entire ocean ecosystem would be disrupted. The atmosphere would change. More heat means more evaporation, more water vapor in the air. This could create a runaway greenhouse effect. The planet could become like Venus, with surface temperatures hot enough to melt lead. But wait, there's more. What about gravity? 2 suns would create a complex gravitational field. Earth's orbit would be affected immediately. If the second sun appeared suddenly, Earth would be pulled in a new direction. The orbit would become unstable. Earth might spiral inward, getting closer and closer to the suns until it's consumed. Or it might be flung outward, becoming a frozen world far from any star. The most likely scenario is that Earth's orbit would become highly elliptical. Sometimes we'd be close to the suns, experiencing extreme heat. Sometimes we'd be far away, experiencing extreme cold. The planet would swing between these extremes as it orbits. The length of a year would change. Currently, Earth takes 365 days to orbit the Sun. With 2 suns, the orbital period would depend on how we're orbiting. If we orbit both stars, the year might be longer. If we orbit just one, it might be similar. But the orbit would be unstable, so it would keep changing. Earth's rotation might be affected too. The gravitational pull from two suns could create tidal forces that slow down or speed up Earth's rotation. Days might become longer or shorter. The planet might even start to wobble on its axis. The Moon would be affected. The Moon orbits Earth, but it's also affected by the Sun's gravity. With a second sun, the Moon's orbit would become more complex. It might be pulled away from Earth. Or it might crash into Earth. Or its orbit might become so elliptical that it swings far away, and then comes close again. The day and night cycle would be completely different. With two suns, there might not be a true night, or night might only happen when both suns are below the horizon. The length of day and night would change constantly. If the two suns orbit each other closely, there might be patterns. When both suns are in the sky, it's day. When one sets but the other is still up, it's still day, but maybe dimmer. When both set, it's night. But these patterns would change as the suns orbit each other. The seasons would be affected. Earth's seasons come from our tilted axis. As we orbit, different parts of the planet tilt toward or away from the sun. But with two suns pulling on Earth, the tilt might change. Or the orbit might become so elliptical that distance from the suns matters more than tilt. Some parts of the year might be incredibly hot when we're close to both suns. Other parts might be incredibly cold when we're far away. The temperature swings could be extreme, hundreds of degrees difference between the hottest and coldest times. The weather would change dramatically. More heat means more energy in the atmosphere. This would create stronger storms, more intense hurricanes, and more extreme weather events. The jet streams would change. Weather patterns would become unpredictable and chaotic. The magnetic field might be affected. Earth's magnetic field protects us from solar radiation. But with two suns sending out solar wind, the magnetic field might be overwhelmed. More radiation would reach the surface. This would increase the risk of cancer and other health problems. It would also damage electronics and power grids. Not all effects would be bad though. Some plants might thrive with more light. Photosynthesis could increase, but only if the plants don't get too hot. Most plants have an optimal temperature range. Too hot, and they die. Some animals might adapt. Nocturnal animals might struggle if there's no true night. But diurnal animals, active during the day, might benefit from longer days. Migration patterns would change. Animals would move to find suitable temperatures. Humans would face enormous challenges. We'd need to adapt quickly. We'd need new technologies to stay cool, to grow food, to protect ourselves from radiation. We'd need to move away from coastal areas as sea levels rise. We'd need to find new sources of fresh water as ice caps melt. If a second sun appeared suddenly, the changes would be too fast. There wouldn't be time to adapt. Most life on Earth would die. The planet would become uninhabitable. However, if the second sun appeared gradually, over millions of years, life might have time to adapt. New species might evolve. Ecosystems might find new balances. But Earth would still be a very different place. Actually, let's think about this differently. What if Earth had always had two suns? What if our solar system had always been a binary system? In that case, life might have evolved very differently. Or it might not have evolved at all. For life to exist, a planet needs to be in the habitable zone. This is the distance from a star where temperatures are just right for liquid water. Not too hot, not too cold, just right, like Goldilocks. With one sun, the habitable zone is a specific distance. With two suns, the habitable zone is more complex. It depends on the brightness and distance of both stars. The zone might be larger, or it might be smaller, or it might not exist at all. If Earth had always been in a binary system, it might never have developed life. Or life might have developed in a completely different way. We might not exist. Or we might be completely different creatures, adapted to a world with two suns. But we don't live in that world, we live in a world with one sun. And that's probably a good thing. Our sun is stable. Our orbit is stable. Our climate, while changing, is relatively stable. This stability allowed life to evolve and thrive. So while imagining two suns is fun, and while planets with two suns do exist, our single sun is perfect for us. It's the right size, the right temperature, and the right distance. It's been shining steadily for billions of years, and it will keep shining for billions more. But you know what? Understanding what would happen with two suns helps us appreciate what we have. It helps us understand how special our sun is. And it helps us understand the universe better. Let's learn more about stars themselves. How do they form? How do they work? What makes them shine? Understanding stars will help us understand our sun, and what it would mean to have two of them. Chapter 4: Life Under Two Suns. How everything would change. Imagine waking up tomorrow and seeing two suns in the sky. What would happen to life on Earth? Let's think about this carefully. Plants would be the first to feel the change. Plants need sunlight to make food. This process is called photosynthesis. But plants also need the right temperature. Too hot, and they can't function properly. Their enzymes break down. Their cells get damaged. They die. Photosynthesis is a delicate process. It requires just the right amount of light. Too little, and plants can't make enough food. Too much, and the process becomes inefficient. Most plants have evolved to work best with the amount of light we get from one sun. Doubling that light would overwhelm their systems. Plants also have temperature limits. Most plants can't survive above 113 degrees Fahrenheit. At that temperature, their proteins start to denature or unravel. This is like cooking an egg. Once the proteins change shape, they can't go back. The plant dies. With two suns, most plants would get too much light and too much heat. They'd wither and die. Crops would fail. Forests would burn or die. Grasslands would turn to desert. The entire plant kingdom would collapse. But it's not just the heat that would kill plants. The increased ultraviolet radiation would also be damaging. UV light can break down DNA and other important molecules. Plants have some protection against UV, but it's designed for the levels we get from one sun, double the UV, and many plants would suffer genetic damage. The increased light would also affect plant growth cycles. Many plants use day length to know when to flower, when to drop leaves, when to go dormant. With two suns, the day length would be different and unpredictable. Plants wouldn't know when to do what. Their internal clocks would be confused. But some plants might survive. Cacti and other desert plants are adapted to intense heat and light. They might thrive, but they'd be the exception, not the rule. Most of Earth's plant life would disappear. Without plants, the food chain would collapse. Herbivores, animals that eat plants, would have nothing to eat. They'd starve. Carnivores, animals that eat other animals, would also starve as their prey disappears. The entire ecosystem would collapse. But wait, what about the oceans? Ocean plants, like algae and phytoplankton, also need sunlight. But they also need the right temperature. Warmer water holds less oxygen. Many ocean plants would die. The entire ocean food web would collapse. Some life might survive in the deep ocean, where it's always dark and cold, but even there, the changes would be felt. The ocean currents would change. The chemistry of the water would change. Life would struggle everywhere. Animals would face multiple challenges. First, the heat. Most animals have an optimal temperature range. Too hot, and they can't function. They'd need to find ways to cool down, or they'd die. Second, the disrupted day-night cycle. Many animals rely on the regular cycle of light and dark. Their internal clocks, called circadian rhythms, depend on it. With two suns, these rhythms would be disrupted. Animals wouldn't know when to sleep, when to hunt, when to migrate. Nocturnal animals active at night would be especially affected. If there's no true night, they might not be able to function. They'd be exposed to predators. They'd struggle to find food. Many would die. Diurnal animals, active during the day, might benefit from longer days, but only if they can handle the heat. Most would need to find shade or water to cool down. They'd need to change their behavior completely. Migration patterns would change. Animals migrate to follow food, to find suitable temperatures to breed. With two suns, the temperature patterns would be completely different. Animals would need to find new migration routes, or they'd die. Hibernation would be affected. Many animals hibernate during cold winters. But with two suns, winters might not be cold anymore, or they might be extremely cold when Earth is far from the suns. The timing would be unpredictable. Animals wouldn't know when to hibernate or when to wake up. Reproduction would be affected. Many animals time their breeding with seasons. But with two suns, the seasons would be chaotic. Animals might not know when to breed, or they might breed at the wrong time, when conditions aren't right for raising young. Humans would face enormous challenges. First, the heat. We'd need to stay cool. Air conditioning would become essential, not optional. But with power grids potentially failing due to increased solar radiation, air conditioning might not work. We'd need new ways to stay cool. Second, food. With most plants dying, and most animals dying, we'd have a food crisis. We'd need to find new ways to grow food. Maybe in underground farms with artificial light. Maybe by genetically engineering crops to handle extreme heat. But this would take time, and we might not have time. Third, water. With ice caps melting and sea levels rising, fresh water sources would be affected. Some areas would flood, others would dry up. We'd need new ways to get fresh water. Desalination plants might become essential. Fourth, health. Increased solar radiation would increase the risk of skin cancer and other health problems. We'd need to protect ourselves. But going outside would become dangerous. We'd need to stay indoors or wear protective clothing. Fifth, infrastructure. Rising sea levels would flood coastal cities. Extreme weather would damage buildings and roads. Power grids would fail. Communication systems would break down. Society as we know it would collapse. Humans are adaptable though. We've survived ice ages, plagues and wars. We might find ways to survive with two suns. But it would require enormous changes to how we live. We might need to move underground, where it's cooler. We might need to build domed cities with climate control. We might need to develop new technologies to grow food, generate power, and stay cool. We might need to change our entire way of life. But if the second sun appeared suddenly, we wouldn't have time for these changes. The collapse would be rapid. Most humans would die. The few survivors would need to adapt quickly, or die too. However, if the second sun appeared gradually, over thousands or millions of years, we might have time to adapt. We might develop new technologies. We might evolve new behaviors. We might find ways to survive and even thrive. But Earth would still be a very different place. The climate would be different. The geography would be different. The life that exists would be different. It would be a new world, shaped by two suns instead of one. Actually, let's think about this from a different angle. What if life had evolved under two suns from the beginning? What if Earth had always been in a binary star system? In that case, life might have evolved very differently. Plants might have evolved to handle intense light and heat. Animals might have evolved different behaviors. Humans might not exist at all, or we might be completely different. Life is incredibly adaptable. Given enough time, it can adapt to almost any conditions. But it needs time. Sudden changes are usually fatal. Gradual changes allow for adaptation. So while imagining two suns is fascinating, and while it helps us understand our own world better, we should be grateful for what we have. Our single sun is perfect for life as we know it. It's stable, predictable, and just right. But understanding what would happen with two suns helps us appreciate our sun. It helps us understand how special our solar system is, and it helps us understand the universe. Let's learn more about stars. How do they form? How do they work? What makes them shine? Understanding stars will help us understand our sun and what it would mean to have two of them. Chapter 5: The Science of Stars. How they work and why they shine. Stars are amazing. They're huge balls of hot gas, shining with their own light. But how do they work? Let's find out. Stars form from clouds of gas and dust in space. These clouds are called nebulae. The word nebula comes from Latin and means cloud. Nebulae are mostly hydrogen, with a little bit of helium and other elements. They also contain tiny grains of dust, made of carbon, silicon, and other materials. Nebulae can be huge. Some are hundreds of light-years across. A light-year is the distance light travels in 1 year, about 6 trillion miles. So these clouds are enormous. But they're also very thin. The gas is so spread out that it's almost a vacuum compared to Earth's atmosphere. Over millions of years, gravity pulls the gas and dust together. The cloud gets denser and denser. It starts to collapse under its own weight. This collapse can be triggered by various events. Sometimes it's a nearby supernova explosion, sending shock waves through the cloud. Sometimes it's the collision of two clouds. Sometimes it's just random fluctuations in density. As the cloud collapses, it fragments into smaller pieces. Each piece can become a star, or a group of stars. This is why stars often form in clusters, hundreds or thousands of them together. Our sun was probably born in such a cluster, but its siblings have long since drifted away. As the cloud collapses, it heats up. The pressure increases. The temperature rises. This happens because of the conservation of energy. As the gas falls inward, its gravitational potential energy is converted into kinetic energy, which becomes heat. The center of the collapsing cloud gets hotter and hotter. Eventually, the center gets so hot and so dense that nuclear fusion begins. Hydrogen atoms start fusing together to make helium. This releases enormous amounts of energy. The energy pushes outward, balancing the inward pull of gravity. When this balance is reached, a star is born. The process takes time. For a star like our Sun, it takes about 10 million years from the start of collapse to the beginning of fusion. That might sound like a long time, but it's actually pretty fast in cosmic terms. The universe is 13.8 billion years old, so 10 million years is just a blink of an eye. The energy from nuclear fusion pushes outward, balancing the inward pull of gravity. This balance keeps the star stable. As long as there's fuel to burn, the star will keep shining. Stars come in different sizes. The smallest stars are red dwarfs. They're about 10% the mass of our Sun. They're dim and cool, but they live for trillions of years. The largest stars are blue supergiants. They can be 100 times the mass of our Sun. They're bright and hot, but they only live for a few million years. Stars also come in different colors. The color depends on the temperature. Hot stars are blue or white. Cool stars are red or orange. Our Sun is yellow-white, which means it's medium temperature. Stars are classified by their spectral type. This is a system that uses letters O, B, A, F, G, K, M. O stars are the hottest and bluest. M stars are the coolest and reddest. Our Sun is a G-type star. It's right in the middle. Stars spend most of their lives on the main sequence. This is when they're fusing hydrogen into helium in their cores. Our Sun has been on the main sequence for about 4.6 billion years. It will stay there for another 5 billion years. When a star runs out of hydrogen fuel, it starts to change. Small stars, like red dwarfs, just fade away slowly. They become white dwarfs, cooling over billions of years. Medium-sized stars, like our Sun, expand into red giants. They grow huge, hundreds of times their original size. Then they shed their outer layers, creating beautiful planetary nebulae. The core collapses into a white dwarf. Large stars have more dramatic deaths. They explode as supernovas. These explosions are among the most energetic events in the universe. They can outshine entire galaxies. The core collapses into a neutron star or a black hole. But let's focus on our Sun. It's a main sequence star. It's fusing hydrogen into helium. Every second, it converts about 600 million tons of hydrogen into about 596 million tons of helium. The missing 4 million tons are converted into energy, according to Einstein's famous equation, E equals mc squared. This energy travels outward from the core. It takes thousands of years to reach the surface. Then it escapes as light and heat, traveling through space at the speed of light. It takes 8 minutes to reach Earth. The Sun's core is incredibly hot and dense. The temperature is about 27 million degrees Fahrenheit. The pressure is about 250 billion times the pressure at sea level on Earth. Under these conditions, nuclear fusion can occur. The Sun's surface, called the photosphere, is much cooler. It's about 10,000 degrees Fahrenheit. This is where the light we see comes from. Above the surface is the chromosphere, a thin layer of hot gas. Above that is the corona, the Sun's outer atmosphere. The corona is a mystery. It's much hotter than the surface, reaching millions of degrees. Scientists aren't sure why. It might be related to the Sun's magnetic field. The magnetic field creates loops and arcs in the corona, heating the gas to incredible temperatures. The Sun has a magnetic field. It's created by the movement of charged particles in the Sun's interior. The field is complex and constantly changing. It creates sunspots, solar flares, and coronal mass ejections. Sunspots are dark patches on the Sun's surface. They're cooler than the surrounding area, but still incredibly hot. They appear in pairs, with opposite magnetic polarities. They come and go in cycles, with a peak about every 11 years. Solar flares are sudden bursts of energy. They can release as much energy as millions of atomic bombs. They're caused by the sudden release of magnetic energy. They send out X-rays and other radiation, and can disrupt satellites and power grids on Earth. Coronal mass ejections are huge bubbles of gas and magnetic field. They're ejected from the Sun's corona. They can contain billions of tons of material, traveling at millions of miles per hour. The fastest ones can reach speeds of 2,000 miles per second. That's incredibly fast. They can reach Earth in just a day or two. When a coronal mass ejection reaches Earth, it can cause geomagnetic storms. These storms can disrupt power grids, damage satellites, and create beautiful auroras. The largest geomagnetic storm on record was the Carrington event in 1859. If a similar event happened today, it could cause trillions of dollars in damage. Coronal mass ejections are different from solar flares. Flares are bursts of radiation that travel at the speed of light. They reach Earth in about 8 minutes. Coronal mass ejections are clouds of particles that travel much slower. They can take days to reach Earth, but they carry much more energy and can cause more damage. The Sun constantly sends out a stream of particles called the solar wind. These particles travel through space at hundreds of miles per second. They're mostly protons and electrons. The solar wind is always flowing, but its speed and density vary. During solar maximum, when there are more sunspots, the solar wind is stronger and more variable. When the solar wind reaches Earth, it interacts with our magnetic field. Most particles are deflected around the planet, but some get trapped in the magnetic field and spiral toward the poles. When they hit the atmosphere, they create beautiful auroras, the northern and southern lights. Auroras are one of nature's most beautiful displays. They appear as dancing curtains of light in the sky, usually green, but sometimes red, blue or purple. Green auroras are the most common. They're caused by oxygen atoms at altitudes of 60 to 200 miles. Red auroras are rarer and occur at higher altitudes, above 200 miles. Blue and purple auroras are caused by nitrogen and are less common. The best places to see auroras are near the poles, in places like Alaska, Canada, Scandinavia, and Antarctica. But during strong geomagnetic storms, auroras can be seen much farther from the poles. In 1859, during the Carrington event, auroras were seen as far south as Cuba and Hawaii. People thought the world was ending because the sky was on fire. The Sun rotates, but not like a solid ball. Different parts rotate at different speeds. At the equator, it takes about 25 days to complete one rotation. Near the poles, it takes about 35 days. This differential rotation helps create the Sun's complex magnetic field. The Sun is moving through space. It's orbiting the center of our galaxy, the Milky Way, at about 514,000 miles per hour. But it takes about 225 million years to complete one orbit. This is called a galactic year. The Sun is about 4.6 billion years old. That's middle-aged for a star. It will keep shining for about another 5 billion years. Then it will start to change. It will expand into a red giant, engulfing Mercury and Venus. Earth might survive, but it will be scorched. Then the Sun will shrink into a white dwarf, cooling over billions of years. But we don't need to worry about that. It's billions of years in the future. For now, the Sun is stable and perfect for life on Earth. Understanding stars helps us understand our Sun. And understanding our Sun helps us understand what it would mean to have two suns. Two suns would mean twice the energy, twice the gravity, and twice the complexity. It would be amazing to see, but it would create enormous challenges for life on Earth. While imagining two suns is fascinating, we should appreciate what we have. Our single sun is perfectly suited for life on Earth. Chapter 6. Latest discoveries and mysteries. What we're still learning about the Sun. Scientists are still learning about the Sun. Every year, new discoveries are made. New mysteries are uncovered. Let's explore some of the latest findings. The Parker Solar Probe is one of the most exciting missions. Launched in 2018, it's getting closer to the Sun than any spacecraft before. It's designed to study the solar wind, the corona, and the Sun's magnetic field. The probe is named after Eugene Parker, the scientist who first predicted the existence of the solar wind in the 1950s. The Parker Solar Probe is an incredible piece of engineering. It has a special heat shield made of carbon composite material. The shield is only 4.5 inches thick, but it can withstand temperatures up to 500 degrees Fahrenheit. The side facing the Sun gets incredibly hot, but the instruments behind the shield stay at room temperature. The probe uses Venus's gravity to slow down and get closer to the Sun. It will make multiple flybys of Venus over several years, each time getting a little closer. Eventually, it will be just 3.8 million miles from the Sun's surface. That's closer than Mercury, which is about 36 million miles from the Sun. The probe has already made amazing discoveries. It found that the solar wind is much more complex than we thought. There are fast streams and slow streams. There are waves and turbulence. The wind accelerates as it leaves the Sun, but we're not sure why. The probe has detected switchbacks, sudden reversals in the magnetic field, that cause the solar wind to change direction. These switchbacks might be key to understanding how the solar wind is accelerated. The probe has also discovered that the Sun's magnetic field is much more complex near the surface than we expected. The field lines twist and turn in ways that create microjets, tiny bursts of energy. These microjets might be heating the corona, solving one of the Sun's biggest mysteries. The probe will continue its mission for several more years, getting closer and closer to the Sun. Each orbit will reveal new secrets about our star. The data it collects will help us understand space weather better, which is important for protecting satellites and astronauts. The Solar Orbiter is another exciting mission, launched in 2020 by the European Space Agency. It's studying the Sun from a different angle. It's the first mission designed to take pictures of the Sun's poles. This is important because we've never seen the poles before. All our previous observations have been from Earth's perspective, which is in the same plane as the Sun's equator. The Solar Orbiter uses a different approach than the Parker Solar Probe. Instead of getting very close, it's going to tilt its orbit to get above and below the Sun. This will allow it to see the poles for the first time. The poles are important because that's where the Sun's magnetic field lines converge, and where the next solar cycle begins. The orbiter has already made discoveries. It found that the Sun's poles are different from the equator. The magnetic field is structured differently there. There are features we've never seen before. This is helping us understand how the Sun works, and how the magnetic field is generated. The orbiter will keep studying the Sun for years to come. It will help us understand the solar cycle, sunspots, and solar flares. It will help us predict space weather, which affects satellites and power grids on Earth. Together with the Parker Solar Probe, these missions are revolutionizing our understanding of the Sun. Ground-based telescopes are also making important discoveries. The Daniel K. Inouye Solar Telescope in Hawaii is the world's largest solar telescope. It has a 4-meter mirror, and can see details on the Sun's surface as small as 20 miles across. That's like being able to see a penny from 100 miles away. The telescope has already revealed amazing details about sunspots. It can see the fine structure inside sunspots, including the penumbra, the lighter region around the dark center. It can see how magnetic field lines emerge from the Sun's interior and create these dark patches. The telescope is also studying the Sun's magnetic field in incredible detail. It can measure the strength and direction of the field at different locations. This is helping scientists understand how the field is generated, and how it creates solar activity, like flares and coronal mass ejections. Space-based observatories are also contributing. The Solar Dynamics Observatory, launched in 2010, takes high-resolution images of the Sun every few seconds. It studies the Sun in multiple wavelengths of light, from visible to ultraviolet to X-rays. This allows scientists to see different layers of the Sun and understand how they interact. The observatory has captured amazing videos of solar flares, coronal mass ejections, and other solar activity. These videos help scientists understand the dynamics of these events and how they affect Earth. The data from these observatories is freely available to anyone. allowing citizen scientists and students to study the sun too. But there are still many mysteries. Why is the corona so hot? The surface is 10,000 degrees, but the corona is millions of degrees. This shouldn't be possible. Heat should flow from hot to cold, not the other way around. Scientists think it might be related to the magnetic field, but we're not sure. One theory is that magnetic waves are heating the corona. These waves are created by the sun's rotation and convection. They travel up through the atmosphere, carrying energy. When they reach the corona, they might be converted into heat. But we're not sure exactly how this works. Another theory is that nanoflares are heating the corona. Nanoflares are tiny versions of solar flares. They're too small to see individually, but there might be millions of them happening all the time. Together, they could provide enough energy to heat the corona. But we haven't detected them yet, so this is still just a theory. Why does the sun have cycles? The sunspot cycle is about 11 years. But why? What causes it? We know it's related to the magnetic field, but the exact mechanism is still a mystery. What causes solar flares? We know they're related to magnetic fields, but we can't predict when they'll happen. If we could predict them, we could protect satellites and power grids better. Scientists are working on this, using artificial intelligence to analyze solar data and look for patterns that might predict flares. What is the solar wind made of? We know it's mostly protons and electrons, but there are other particles too. There are also alpha particles, which are helium nuclei. There are traces of heavier elements like carbon, nitrogen and oxygen. Where do they come from? How are they accelerated? These are still open questions. The solar wind has two main components, the fast solar wind and the slow solar wind. The fast wind comes from coronal holes and travels at 500 to 800 kilometers per second. The slow wind comes from other regions and travels at 300 to 500 kilometers per second. Why are they different? We're not entirely sure. These are just a few of the mysteries. There are many more. Why does the sun have a magnetic field? How is it generated? Why does it flip every 11 years? How do sunspots form? Why do they appear in cycles? How do solar flares release so much energy so quickly? These questions drive scientists to keep studying, keep exploring, keep learning. But that's what makes science exciting. There's always more to learn. Every answer leads to new questions. Every discovery reveals new mysteries. The sun has been studied for thousands of years, and we're still learning new things about it. That's the beauty of science. It's a never-ending journey of discovery. Recent discoveries have also revealed new things about the sun. For example, scientists have found that the sun might be smaller than we thought. New measurements suggest it might be slightly smaller than previous estimates. This doesn't change much, but it's interesting. It shows that even basic properties of the sun can be refined with better measurements. Scientists have also found that the sun might be older than we thought. New calculations suggest it might be 4.6 billion years old, not 4.5 billion. Again, this doesn't change much, but it's a refinement of our understanding. As measurement techniques improve, we get more accurate data. The sun's magnetic field is more complex than we thought. It's not just a simple dipole like a bar magnet. It has multiple poles, and they change over time. The field is constantly twisting and turning, creating complex patterns. Understanding these patterns is key to understanding solar activity. Sunspots are more complex too. They're not just dark patches, they have structure. They have magnetic fields. They can create solar flares and coronal mass ejections. Understanding them better will help us understand the sun. Recent observations have revealed fine structure inside sunspots that we didn't know existed. The solar cycle is more complex than we thought, It's not just 11 years. There are longer cycles too. There might be cycles of 22 years, 88 years, and even longer. These cycles might be related to the Sun's motion through the galaxy. As the Sun orbits the galactic center, it might pass through regions with different densities of gas and dust, which could affect its activity. The Sun is connected to the rest of the universe. It's affected by the galaxy's magnetic field. It's affected by cosmic rays from other stars. It's part of a larger system, not isolated. Understanding these connections helps us understand the Sun better, and it helps us understand our place in the universe. Despite all the mysteries, we know a lot about the Sun. We know how it works, we know how it formed, we know how it will die, we know it's essential for life on Earth. We know that having two suns would be very different. It would create challenges, it would change everything, but it would also be amazing to see. As we learn more about the Sun, we learn more about stars in general, we learn more about the universe, and we learn more about our place in it. The Sun is just one star among billions, but to us, it's special. It's our star. It's the star that makes life possible. So while imagining two suns is fun, and while it helps us understand our world better, we should appreciate what we have. Our single sun is perfectly suited for life on Earth. It's been here for billions of years, and it will be here for billions more. The mysteries remain. Why is the corona so hot? What causes solar flares? How does the magnetic field work? These questions drive scientists to keep studying, keep exploring, keep learning. And that's what science is all about. Asking questions, finding answers, discovering new mysteries. It's a never-ending journey of discovery. Before we finish, let me share a few more remarkable facts about the Sun. The Sun contains 99.86% of all the mass in the solar system. Everything else, all the planets, moons, asteroids and comets, makes up just 0.14%. The Sun is truly the king of the solar system. The Sun's energy output is so enormous that if you could capture all the sunlight hitting Earth for just 1 hour, it would be enough to power the entire world for a year. Unfortunately, we can't capture it all, but we're getting better at using solar energy. Solar panels are becoming more efficient and cheaper, allowing us to harness the Sun's power. The Sun is actually moving through space, it's not sitting still. It's orbiting the center of the Milky Way galaxy at about 514,000 miles per hour. But the galaxy is so huge that it takes about 225 million years to complete one orbit. This is called a galactic year. The last time the Sun was in this position, dinosaurs were just beginning to appear on Earth. The Sun's magnetic field is incredibly powerful. At the surface it's about 1 Gauss, which is about twice as strong as Earth's magnetic field. But in sunspots the field can be 3,000 times stronger. That's strong enough to affect the path of charged particles, and create all sorts of interesting phenomena. The Sun produces neutrinos, tiny particles that barely interact with matter. Billions of neutrinos from the Sun pass through your body every second, and you don't even notice. They're passing through Earth, through you, through everything, all the time. They're like ghosts, invisible and almost undetectable, but they're everywhere. The Sun also produces gravitational waves, though they're incredibly weak. These are ripples in space-time, caused by the Sun's mass and motion. We can't detect them yet, but future instruments might be able to. They would give us a new way to study the Sun and understand its internal structure. The Sun's surface is covered in granules, small cells of hot gas that rise and fall. Each granule is about the size of Texas, and lasts for about 8 to 20 minutes. There are millions of them covering the Sun's surface, constantly churning and moving. They're like bubbles in a pot of boiling water, but on a scale that's hard to imagine. The Sun also has supergranules, which are much larger. They're about 20,000 miles across and can last for a day or two. They're caused by larger-scale convection patterns in the Sun's interior. Understanding these patterns helps us understand how heat moves through the Sun. The Sun's rotation creates something called the solar dynamo. This is the process that generates the Sun's magnetic field. It's driven by the differential rotation, the fact that different parts of the Sun rotate at different speeds. This creates electric currents, which in turn create magnetic fields. It's a complex process that we're still trying to fully understand. The Sun also has something called the tachocline, a thin layer between the radiative zone and the convective zone. This is where the Sun's rotation changes dramatically. It's thought to be important for the solar dynamo and the generation of the magnetic field. But it's deep inside the Sun, so it's hard to study directly. These are just a few of the amazing facts about the Sun. There are many more. The Sun is a complex, dynamic object that we're still learning about. Every discovery reveals new mysteries. Every answer leads to new questions. That's what makes studying the Sun so exciting. Despite all the mysteries, we know a lot about the Sun. We know how it works, we know how it formed, we know how it will die, we know it's essential for life on Earth, and we know that having two suns would be very different. It would create challenges, it would change everything. But it would also be incredible to see. The sky would be brighter. The sunrises and sunsets would be spectacular. But the temperature would rise, the climate would change, life would struggle. It would be a very different world. But we don't have to worry about that. Our Sun is perfectly suited for life. It's stable and predictable. It's been shining for billions of years, and it will keep shining for billions more. It provides just the right amount of light and heat for life to thrive. We are incredibly lucky to have it. We've learned so much about the Sun in this journey. We've learned about its size, its composition, its structure. We've learned about nuclear fusion, the process that powers it. We've learned about sunspots, solar flares, and coronal mass ejections. We've learned about the solar wind and auroras. We've learned about planets with two suns, and what it would mean for Earth. Most importantly, we've learned to appreciate what we have. Our Sun is special, it's our star. It's the star that makes life possible. Without it, Earth would be a frozen, lifeless rock. With it, Earth is a vibrant, living world, full of plants, animals, and people. The Sun has been our constant companion for billions of years. It was here before life began. It will be here long after we're gone. It's been shining steadily, providing light and heat, making life possible. It's the most important object in our solar system, and we're lucky to have it. Every day, researchers are learning new things about the Sun. New missions are being planned. New telescopes are being built. New discoveries are being made. The Sun continues to surprise us, to teach us, to inspire wonder. That's what makes studying it so fascinating. So the next time you see the Sun, take a moment to appreciate it. Think about how remarkable it is. Think about how essential it is. Think about the journey that light took to reach your eyes. Think about the billions of years it's been shining. Think about how fortunate we are to have such a perfect star. Wow, what a journey we've been on. We've explored what would happen if two suns rose tomorrow. We've learned about our amazing Sun. We've met planets with two suns. We've discovered the science behind stars. We've learned that having two suns would be incredible to see, but it would create enormous challenges. The temperature would rise. The climate would change. Life would struggle to adapt. Earth would become a very different place. The oceans would heat up. The ice caps would melt. The weather would become extreme. Most life would die. It would be a catastrophe. But we've also learned that our single sun is perfect. It's the right size, the right temperature, and the right distance. It's stable and predictable. It's been shining for billions of years, and it will keep shining for billions more. It provides just the right amount of light and heat for life to thrive. We are incredibly lucky to have it. We've learned about stars, how they form from clouds of gas and dust, how they shine through nuclear fusion, how they come in different sizes and colors, how they live and die. We've learned that our sun is just one star among billions, but it's special to us. We've learned about the latest discoveries. The Parker Solar Probe is getting closer to the sun than ever before. The Solar Orbiter is seeing the sun's poles for the first time. Ground-based telescopes are revealing incredible details. We're learning more about the sun every day. We've learned about the mysteries that remain. Why is the corona so hot? What causes solar flares? How does the magnetic field work? These questions drive scientists to keep studying, keep exploring, keep learning. Science is a never-ending journey of discovery. We've learned about planets with two suns. They exist. They're real. Kepler-16b orbits two stars. From its surface you would see two suns in the sky, two sunrises, two sunsets. How amazing would that be? But these planets face challenges that Earth doesn't have to deal with. Most importantly, we've learned to appreciate what we have. Our sun is special. It's our star. It's the star that makes life possible. Without it, Earth would be a frozen, lifeless rock. With it, Earth is a vibrant, living world. That's something to be grateful for. So the next time you see the sun, whether it's rising in the morning or setting in the evening, take a moment to appreciate it. Think about how amazing it is. Think about how essential it is. Think about how lucky we are to have it. Think about the journey that light took, from the sun's core tens of thousands of years ago, to reach your eyes today. And remember, while imagining two suns is fun, our single sun is exactly what we need. It's been here for billions of years, and it will be here for billions more. Thank you for joining me on this journey. I hope you learned something new. I hope you learned about our amazing sun. I hope you learned about stars and planets and the universe. I hope you're curious to learn more, and I hope you'll keep exploring, keep asking questions, and keep discovering. Science is full of questions, and that's what makes it awesome. There's always more to learn, more to discover, more to explore. The universe is vast and mysterious, and we're just beginning to understand it. The sun has been shining for billions of years. It will keep shining for billions more. And we'll keep learning about it, discovering its secrets, and appreciating its beauty. It's our star, and it's amazing. I'm Sleepy, and this was your science story for today. Sweet dreams, and keep looking up at the stars. Remember, every time you see the sun, you're seeing a star that's been shining for billions of years, providing light and heat for life on Earth. That's pretty special. Good night.